Okay, it's 4 o'clock, so let's go ahead and get started today. All right, happy Thursday, everybody. So it's been a while since I've seen you all, or at least seen your names on my computer screen, right? So something has changed since the last time. So as you can see, I'm in my apartment now. I'm no longer on campus. So due to the executive order from the governor, they're basically telling everyone just to work from home. So you can see a little bit of my personal life here. So this is my apartment. Nothing too fancy yet. But it is what it is. And you'll notice that I'm in my pajamas right now. So if I'm going to work from home, I don't really see the need to kind of dirty a good shirt when I'm just going to be in my pajamas all day anyway. So in my comfy slippers and my comfy pajama pants. So ready to do some finite elements. Okay. So today we have a lecture planned. So we're going to be talking about mesh convergence today. Right. So it's going to be a really important topic. So especially one that's going to be that I want you guys to do for your projects. Right. First of all, let me just ask, how's everyone doing? Hopefully everyone is taking to the quarantine well. All right, that's good. Yeah. Hopefully, oh wow. Oh, nice. Yeah, so yeah, hopefully everyone's in a safer place right now. Definitely now is a good time to be at home where it's safe and do all the social distancing and all that, because it's the situation I think escalates every single day. So we all need to be safe. So it's good. Hopefully you guys are all in a much better place. Took advantage of the all the non-instructional days that we had, and prepared to basically kind of sit this out until things are safer, right? So I don't know if we talked about this last time, but basically the update now is that we're going to be in virtual mode basically for the rest of the semester. So basically all the lectures from now on will be from my living room. So we're not going to be able to go back to campus. I have a couple announcements with respect to that. We've already talked about as a class that we're going to cancel our second midterm kind of in favor of more ANSYS activities. But I've been doing a lot of thinking about it over the last few days, and what I realized was that I think one thing that's going to be useful for you guys for both your projects and for using ANSYS professionally is for us to do kind of a lot more ANSYS activities, because as I start to dive more and more into the software, I think there's a lot of features that we can do that'll be useful to you guys. The first of which we'll do after the spring break, which will be dynamics simulations. So those are simulations with movable parts. So that's going to be exciting. And then I'm looking into also beams and shells. So with that in mind, I have a proposal. So originally, for our final project, there was going to be a final presentation component to it. With as many people as we have in the class right now, we kind of need probably around 2 weeks of class sessions just to get through all the final presentations. So I wanted to ask you guys, so do you guys still want to do a final presentation? I mean, we can do it through Zoom, of course. But if we skip the final presentations, then we have time for one more ANSYS activity at the end. And also just some free time for you guys just to work on the projects. I think, that'll be kind of nice to do as well. I kind of did that last year. So last year I had a couple of weeks where, I just had you guys work, I had the students work on the projects, and I just, kind of walked around and kind of helped people kind of one by one. Okay. So there's a lot of votes for activities. So I think that sounds good. So I had one suggestion come in that says, maybe we'll just upload just a brief PowerPoint just to, just so you can see what everyone did. So I think that's a good idea. So how about we don't have just the in-class presentations anymore, but I'll have everyone at least make a PowerPoint presentation just to kind of briefly summarize what they did. And I'll put that in a place that'll be available to everyone so you guys can see what kind of everyone worked on. That sound good? Okay, all right, so let's do that. So right now, actually prior to that, I had planned two more ANSYS activities for after the spring break. So now that we're not doing the final presentations anymore, let's do 3. Okay, so we're gonna have 3 more ANSYS activities that we're going to do, basically 4, 5, and 6. So I kind of know what I want to do for 4 and 5, and for 6, I kind of need to think about it, but I have some time to think about it. So let's do that. Okay. Okay, so I'll put in an announcement on Titanium just to make it official. So instead of doing final presentations in class, let's have an additional ANSYS activity. So and I think maybe after I read your guys' proposals, then I'll see what you guys are working on, and then I'll make an activity after that. Okay. So the question is there still a project? Yes, you still need to do the project, but instead of doing a final presentation and a report, I'm just gonna have you guys just do the report. And then we're not gonna spend class time to do the presentations. I think it'll be more fun to do another activity, and actually more useful for your project too, because then that'll give us a chance to explore some features of ANSYS that might be useful to you guys. So how about this? So after you guys turn your proposals, and I'll read them over spring break, and then I'll develop some activities that'll be that I think will be useful to a lot of you guys. Aerodynamics of a lobster. We'll see. Yeah, so the report, so you're still going to make a PowerPoint presentation, so that's still going to be there, except instead of presenting it, I'm just going to have you guys upload it, and I'll put it in a place where basically everyone can take a look. Because I think a lot of you guys, at least the ones that I've talked to, you guys are planning to do something really cool. So I want to give everyone a chance to basically see what everyone else has been working on for the final project. Okay. Yeah, so the PowerPoint now I think will be graded based on completion. So I'm not going to take a too careful look at it, but that'll just be your chance to kind of just show off, what everyone else is doing. All right. So the question is, if the proposal was due Monday, and then yes, that's correct. So the proposal originally was due tomorrow, but since I know you guys are working on the activity, and some of you have been running into some issues with the virtual machine, let's have the proposal due Monday, just so you have at least the weekend to think about it too. But if you're done with it already, go ahead and submit it. Remember, it's just based on completion. So, if you already have an idea for what you want to do, then just go ahead and upload it, and I can take a look kind of as soon as I can. Okay. So that was the kind of the big announcement that I had. Are there any questions, before we move forward for today? All right, so the question is, was there a proposal outline? So I uploaded a couple of sample proposals. So the purpose of the proposal was just mostly just to let me know what you're thinking of, what you want to analyze with finite elements. So it's not a formal document. It's just there's kind of just certain elements that I want you to include. So if you look at the couple samples that I posted online, that kind of gives you an idea of what I'm looking for in the proposal. But basically just give me a picture and maybe give me a paragraph about what you want to do. Basically, that's it. All right, any more questions before we start today? Okay, so let's go ahead and get rolling. So the topic today is mesh convergence, right? So it's mostly going to be a lecture, but I do have a couple activities. And when I say activities, they're just kind of small. There's going to be a small Matlab part and a small ANSYS part, but it's nothing you have to turn in. So if you want to follow along, once we get to that part in the lecture, you can go ahead and boot up Matlab and boot up ANSYS, and download the Matlab script and the ANSYS project that I've uploaded on Titanium. But if you just want to just focus on the lecture, you can go ahead and do that, because I'm going to share my screen and kind of show you exactly what I'm going to do in that place, okay? Okay, so the topic today is mesh convergence testing. Okay. So hopefully after today, this will answer kind of one of the most common questions that we've seen, which is how do we determine how many elements to have in the mesh, or the mesh density. Because what we know already is that the amount of elements that we have in the mesh, or how refined our mesh is, it has a big impact on our simulation results, right? So we know that if we have a refined mesh, so when I say refined, I mean that our mesh has a lot of elements, then our results are going to be more accurate. but that accuracy comes at a cost. So, you know, basically the more elements that we have in our mesh, the more computational time and the more memory that your computer is going to need in order to run that simulation. Okay. So the question is, you know, how much do we refine for any given situation, and you know, how much is enough, right? So unfortunately, you know, there's no hard and fast rule for how many elements. There's no kind of magic number. There's no like, you know, you should have at least 50,000 elements, and then your solution will be good. Because of course it's going to depend on the situation. It's going to depend on your geometry. It's going to depend on your loading. Okay. Right. And a lot of times it depends what we're looking for, right? So remember, you know, when we talked about the project, what I told you was that, you know, when you do finite element analysis, it's always done with some kind of objective, right? Usually when you perform a simulation, there's always some kind of quantity that you're always looking for. So in the case of, you know, the activities that we did, you know, one of the things that we're looking for often is the mechanical stress, right? Because a lot of times, you know, when we do structural mechanics simulations and we find the mechanical stress, that'll tell us whether our part is going to break or if it's going to, you know, or not. Okay. So the whole idea with mesh convergence testing is to perform some experiments to basically show that your quantity of interest is converged with the mesh. Or another way to say that is, you know, if we, you know, run the simulation with more elements, then the computation of our quantity of interest is not going to change. Okay. So basically, what we want to show is that computation of quantity of interest does not depend on the mesh. Okay. Right, so the question is, to formally analyze mesh convergence, is it typical to plot similar data points from all different profiles in, say, Matlab? So you don't have to use Matlab, but you will see that it is useful to plot the data. So usually it's more convenient to use something like Excel, just because you know, spreadsheets are kind of built for this, and basically you can get a mesh convergence plot. But we'll get there kind of later in the lecture. And so the way that we are going to show this is with a mesh convergence test. Okay. All right. Any questions on this before I wipe the board? Okay. Okay. So the idea of a mesh convergence test is very simple. So it's kind of a fancy name, but you know, we kind of already have all the tools to do this. So it's not a fancy feature, and it doesn't involve, you know, that much theory. But basically, what you're going to do is you're going to run your finite element simulation multiple times, and each time you run it, you're going to change the mesh density. Okay. And then what you should see, or what you're going to measure each time that you run your finite element simulation, is that you're going to measure your quantity of interest. Okay? And so what you're going to do is you're going to make a table. So on the left column, you're going to put n, where n right here, this is the number of elements. Okay. And on the right-hand column, you have your QOI, which is your quantity of interest. Okay. And then as you refine your mesh, then the number of elements in your mesh are going to increase. And then what you should see is your quantity of interest should start to converge on a single value. Okay. So basically, you're going to run your simulations and basically fill out this this table. Okay. Right. So the idea when you perform a mesh convergence test is that you should start with a relatively coarse mesh. Because a coarse mesh, even though we know it's going to be inaccurate, at least it's going to be, you know, cheap to run. Because, you know, a lot of times when you first look at a problem, you know, you first look at your geometry, you look at your boundary conditions. It's really impossible to tell, you know, just by looking at it, how many elements that you need in order to reach a converged solution. Right? So the idea is to start something with something that's coarse, and then as you gradually refine it, then you'll eventually reach convergence on your quantity of interest. Okay. Right. So let me show you kind of an example how this is, okay? Or just kind of what's in practice, okay? So let's look. So let's take our bike crank as an example. Okay. So our bike crank looks something like that, or at least as best as I can do it, okay? And then you know, as we mesh this bike crank, it might look something like this, right? Right. So now we have a peanut. And so basically, you know, what you're going to do is you're going to run the simulation with different mesh densities. So here we have, say, you know, this is, let's say, our coarse mesh. Okay. Okay. And then we can run the simulation again with a finer mesh. Okay. And then you can, from this, you can measure, let's say, the stress at this location right here. Okay. So we can say that the stress at that kind of dip right there, that's going to be our quantity of interest. Okay. And then once we do that, we can start to fill out our table. Okay. Where remember on the right-hand column we have our quantity of interest, and on the left-hand column we have the number of elements. Okay. So basically, each time we're running the simulation, we're writing down in Excel how many elements were in our mesh, and then what was our quantity of interest. Okay. And then after that, basically, we can make a plot. Okay. So the most common way to, you know, kind of as what was mentioned before, the most common way to kind of present the results from a mesh convergence test is to use a scatter plot. Okay. We're on the x-axis right here. We have the number of elements. Okay. And on the right, on the y-axis here, we have our quantity of interest. Right. And so what you should see is that for coarse meshes, right? So let's say that we start right here. You know, this was kind of our first mesh that we did. And then as we refine the mesh, you know, you might see that your quantity of interest will start to change. Okay. But then eventually you'll reach a point where your quantity of interest doesn't change anymore with the mesh. Okay. So we can connect the dots like that. Okay. So then, you know, let's say that we kind of separate the two regions right here. So on the left of this curve, you can see that, you know, as we refine the mesh, then our quantity of interest is changing. And then on the right, you can see that it's no longer changing. So the question is this graph a log fit? So there's no fit at all. It's just kind of just connect the dots. So it's, you know, a lot of mesh convergences will kind of have this, it looks like a logarithm, but it's really just kind of, you know, you're just kind of connecting the dots on this guy. Okay? So on the left here, we can say that the mesh is not converged. Right? And on the right here, we can say the mesh is converged. Okay? And so the point at which the mesh converges, you can say that that location right there. Okay? So we can say at that location right there, where the we kind of get we kind of maximize the accuracy and kind of minimize the costs. That point right there is kind of the best the best mesh density to run our simulation. Okay? Because we can see that our we can refine the mesh some more, but we kind of get diminishing returns where it doesn't really get that much more accurate, but we're working that much harder. So that's kind of the sweet spot there for the maximum of accuracy with the most minimum of cost, and that's kind of what you're showing with the mesh convergence test. Okay. So that kind of makes sense to everyone. Any questions on this before I wipe the board? Okay. Yeah. So this is kind of the sweet spot. So this that's the spot where you at least want to be. You want to make sure that your mesh is at least at this point right here, right? Of course, when you present your results, you want it to be accurate. So you can definitely use meshes that are kind of past this line as well. But that's kind of at least where you want to be for your mesh. You don't want to have anything that's more coarse than that. Otherwise, your results are going to be inaccurate. Right, so the question is there a quantifiable effective percent as the effective Q of I convergence that is acceptable? So unfortunately, it really depends on kind of the industry that you're in and kind of the tolerances that you have for, and it's going to depend on the company that you work for as well. Because, to a certain extent, there's always going to be a little bit of wiggle in terms of how much that quantity of interest is going to be changing as you refine your mesh. So you're never going to get it quite to be kind of exactly the same as you refine. It really depends on your industry, but some of the numbers that I've seen are things like 5%. 5% is pretty max, but if you can get it less than like 3% or 2% relative change, then that's usually something that's pretty reliable, at least from what I've seen. But of course, I think if you're working in aerospace or you're working in something with a lot closer tolerances, then it's going to be tighter than that. All right, any more questions on this? Okay. All right. So so what I showed you in the last graph was the quantity of interest increasing as we as we go up. Oh, question. How do they determine the goal value? So the goal value, a lot of times you're running a simulation to find out what that quantity of interest is. So that really, the goal value really just it depends on what your physics are. But what you're ultimately looking to confirm with the mesh convergence is that you're looking for that thing to plateau. So it doesn't really matter what that value is, because that's ultimately what you're trying to find out with the finite element simulation. But with the mesh convergence test, you just want to see it plateau. So as you refine the mesh more, then you don't see it change anymore. So the question is, so by percent, do you mean the percent error between the previous value? Yeah, that's basically what I mean. So percent error, that's how much it changed relative to the previous one. So that's, if it's 5% more than the previous one, then, that's kind of what I mean by relative change. Okay. So in the last graph, I showed you that the quantity of interest was kind of increasing as we increase the mesh, but it can come from the opposite direction too, right? Right, so you could very easily have a condition which looks like this. Okay. Where like before the x-axis is n, the number of elements, and then the y-axis is your Q of I. Okay. So it can really come from any direction. So it can come from either above or below. So the only thing that matters is this part right here, which is you want to see that your quantity of interest will plateau. You could even see something that looks like this, depending on your mesh. So you can even see it do something crazy like that. So you might see it jump around kind of up and down like that. But you know, as long as you reach a point where the graph is kind of flattening out, then that's kind of what you're looking for. Okay. So, you know, before we jump into the examples, you know, you know, a lot of times, you know, when you're doing these mesh convergence tests, it's going to seem just like a lot of busy work because you're just kind of changing a number, you're running a simulation, which might takes a while, and then you're jotting things down. So, you know, it's not the most exciting thing to do, but you know, for many practical applications of finite elements, this mesh convergence, it's going to be a must. You know, especially if you're going to be using finite elements to do any kind of professional engineering work, what tends to happen a lot, you know, and you know, this is a very reasonable, you know, way of thinking, is that when people look at your finite element results, they're not going to believe it right away. So there's, you know, in America, you know, we have this thing where you're innocent until proven guilty. For finite elements, it's kind of the opposite. You're kind of guilty until proven innocent, right? So you can present your finite element results, but no one's going to believe you until you kind of provide some proof and kind of persuasion that, you know, what you did was kind of, you know, legit. So we'll talk more about this when we talk about V&V, which is verification and validation after the spring break. But mesh convergence kind of forms a very key component of this. Right? Right? So you think of like a mesh convergence test as kind of some evidence that you can bring to kind of show that, you know, that you perform this finite element simulation well and that you can trust the results. Right? So the question is, the convergent is for one specific method, element, order, and shape. So yeah, that's a great question actually. So, you know, there's actually different ways to do mesh convergence. So, you know, we're going to be focusing most on what's called H convergence, which is the convergence of, you know, you kind of hold the element order and the shape the same, and then you just make the elements kind of smaller and smaller. But, you know, another way that you can achieve accuracy, kind of what we talked about, is you can increase the element order, or you can change the shape to be something that's more appropriate. So that's kind of different ways to go about it. You know, the idea is kind of the same, where you kind of show that, you know, if you change from one method to the other, or you increase the order, then, you know, your simulation results aren't changing that much. But you can do the kind of the same thing. So we're focused mostly on just what's called H convergence. But specifically for changing the element order, that's called P convergence. So that's definitely another way to perform mesh convergence as well. Right. So the question is, in industry, is FEA mainly a supplementary tool for project designs, or do some companies end up relying on the results of a simulation to base a design off of? Yeah, that's a great question. So, so it really depends a lot on the company and the you know, and the way that they do things. So some companies really do see it as mainly just a supplementary tool where they do some other kind of experimental measurements, but they do hand calculations to kind of supplement that. But there are definitely other companies that, you know, where it's kind of impossible to kind of run experiments or to do hand calculations. So they rely on FEA quite a bit to do that. So, you know, basically, you know, and the way that you can kind of tell is that if you know, if your industry deals with some things that are really expensive, like it's like the aerospace industry, then they're going to rely on simulation tools quite a bit. You know, so they rely on things like mesh convergence to basically tell people that, you know, what they're doing is accurate. Yep. All right. Any more questions on this before we jump into an example? Okay. So I have two examples for you guys. The first example I have is in Matlab just because it's kind of a simple case, and it's kind of just to show you exactly what mesh convergence is about. And then I have an example in ANSYS, which is kind of just to show you what you would do like for your project or something. Okay? So let me kind of write out the problem statement here, and then I'll switch to my laptop, which has Matlab on it. So for this example, this is a problem that we did before. So you remember kind of back a few weeks ago, there was a couple class sessions where we implemented a Matlab code to solve a 1D problem. Okay. So we're basically going to be doing the same problem. So I've uploaded kind of a modified version of the script just for this mesh convergence test. So let me just kind of write out what that is again. So in this problem, we have a one-dimensional bar. So this is a heat transfer problem. So on the left side right here, we have a fixed temperature. Our temperature is going to be 50 degrees C. Right? We have some generation that's coming in. Right? So our generation is going to be 30. Our generation function will be S of x equal to 30x. Okay? And then we have a natural boundary condition on the right-hand side. So this is going to be Q out is equal to 600 watts per meter squared.
Professor Tran, does that say T naught?
Yeah, T naught. Yeah, so it's a essential boundary condition on the left-hand side.
Okay, thank you.
Mm-hmm. Okay, and then we have our thermal conductivity. Our thermal conductivity is 50 watts per meter K. And then our cross-sectional area is 0.1. Okay. So we wrote a Matlab script for this. Okay. Okay. And so the script that I've uploaded on Titanium, I've made kind of a small modification just to kind of illustrate what you would do for a mesh convergence. Because remember, when you do mesh convergence, there's always some kind of quantity of interest that you're interested in. So in this case, our quantity of interest is going to be right here, right? So let's say that when we're solving this problem, what we're interested in is solving for the heat flux at this location, right? So basically, what we want to solve for is dt dx here. Okay? So this is going to be our QOI, or quantity of interest. Okay? So I've already kind of implemented for you, so there's nothing for you guys to implement. But if you want to follow along, I'm going to do this in Matlab. Okay. So let me share my my computer screen. Let me close YouTube first. Okay. All right, so if you have, so I don't have the chat right now, so I have it. I can see it on my my iPad. But if you have a question, just turn on your microphone and just shout it out. Okay. Okay. So here we have the Matlab script, right? So basically, what we're going to be modifying is this this value right here. Okay. So remember, what we're ultimately going to be doing is making a table between the quantity of interest and our and the number of elements. Okay, so let's start with the coarse mesh. So let's start with kind of the coarsest mesh that we can imagine, which is 2, right? So we have basically 2 elements, and then let's run our code. Okay. So you can see I've modified the script to kind of tell you what the slope at the midpoint is. Okay. So let's input this data into Excel. Okay. So let's bring up Excel. Right. And let's make 2 columns. We'll make a first column N, and the next column will be our Q of I. Right. So the first one that we did had 2 elements. So we'll do 2 right there. Okay. And then our slope at the midpoint is 13.25. And did I change this? Oh, okay. Let me unmodify that. Yeah. So here's the plot, which you can basically see. Okay. Right. I think I modified something. Let me see. I think I changed the length of the bar. So it shouldn't be that bad. Okay. Oh, the length should be 5. Okay. Okay. Yeah, that's what I thought it was. Okay. So the slope at the middle was 43.25. Sorry about that. I accidentally changed the length of the bar in the script. Okay. Okay. So now that we have the results for n is equal to 2, so let's continue on. So now let's refine our mesh. Right. So we can refine the mesh by increasing the number of elements. So let's increase this to 4. Right. And so let's run our script again. Right. So you can see that once we increase the number of elements to 4, we can see from the graph here that our solution is getting more accurate. So the red curve, which is our finite element curve, is becoming closer and closer to the blue curve, which is the exact one. Right? And you can see the slope at the midpoint is changing as well. Okay? So let's input this data. So we know that we did 4 elements. So our n values are equal to 4. And then our slope at the midpoint is going to be 53 or 57.3125. Okay? So then let's continue to do this. So let's do this for 6. So you can see our slope at the midpoint changed again. You can see our solution getting more accurate, right? So you can see for 6 elements, we have a slope of 61.305556. Let's do 61.3. Okay. Right. So now let's kind of ramp things up just to speed things up a bit. So let's make this equal to 10. Okay. So our grid is getting more and more fine. We have 10 elements across the domain. Okay. So for 10 elements, we have a slope of 64.25. Okay. So now let's do 15. Okay, so for 15 elements, we have a slope of 68.22. Okay.
Dr. Chen?
Yeah.
Is there any thought process behind your ends that you're choosing? Like, or do you just usually kind of go like 2, 4, 15, or 6, 15?
Yeah, that's a great question. So, when you do a mesh convergence test, you want to definitely start gradually. So you don't want to kind of increase it too much because you might miss some kind of interesting behavior. But you can kind of, just kind of have a feel for it. So if you can see it, if it's not really converging, you're changing gradually and it's not plateauing, you can kind of speed up the number, the kind of the increase until you basically see that. And then, if you go back and you can kind of fill in some extra points, but kind of the thought process is to kind of start gradually. But then if you don't see that much changes or you still see it, changing quite a bit, then you can kind of ramp up how quickly you refine it, just so you can kind of reach convergence a little bit faster.
Also, when you talk about the midpoint, if a node, like say you had 2 nodes, if you have the slope there's like a solid line, it's not how do you say it's continuous, but it's not like derivable there. But do you look at a slope with the line to the left or the right, or does that matter? I mean, eventually be the same slope, but if the node is at the midpoint, then there's no slope there, right?
Yeah, that's a great question. So I'm not showing it here, but the way I'm computing the slope is I'm not really deriving a function, but what I'm doing is I'm taking what's called like a finite difference. So I'm basically just taking the difference between the 2 nodes that are closest to the midpoint and then dividing by the distance in between them. So basically assuming that it's a linear line and just computing that slope. But for most problems, you're going to do this in ANSYS. So you're basically going to let ANSYS do it and compute your quantity of interest. So I kind of just kept that behind the curtain. But if you're curious, that was kind of how I did it. Okay, so now we're at 30. So you can see, you know, as we're ramping it up and more, we're getting convergence here. So you can see we're getting very little changes. So let's do just a few more, just for the sake of completeness. So you don't have to go kind of as far as I do, but this is just kind of just to show you if you kind of keep taking it further and further. But you can stop basically once you start seeing things leveling out. Okay? But you have to be careful too, because sometimes you might reach a local minimum or a local maximum. So even if you go from one mesh to another one and things don't change that much, keep going for a couple meshes after that, just to make sure that that trend, you know, wasn't a fluke, and then you're actually seeing it even out, you know, quite a bit.
Can you say that again about the local minimum?
Right.
Like
So
if there's
right. Maybe not local minimum, but you might reach a point where things just aren't changing that much, but it could just be kind of a fluke. That's kind of what I call it. So let's say that you increased from like 6 to 10, okay? And then you saw it change, like you went from 61.3 to 61.4. So it might look like this, something like that, right? So here you're kind of tempted to say, oh, you know, I did 2 consecutive tests, and then the you know, the mesh or the quantity of interest didn't change that much. So it's really tempting at this point to kind of stop right here. But it could be sometimes that, you know, this was just kind of a fluke, and then, you know, things might still continue to change. So keep refining it for a couple more steps after that. And if you see, you know, it could be that you got 61, 61.2, and then your next one could be 68. So you can see, you know, you still have some ways to go until you reach convergence. So it's only if you see, you know, 61, 61.2, 61.2, 61.3. So if you see it not change for 2 or 3 steps in a row, then that's, you know, that's usually pretty reliable right there.
okay.
Yeah. So don't just stop if you see 2 in a row. Wait until you see kind of 3 or 4 in a row before you stop. Oh, I ran that one. And then let's do one more. So let's do 60. Right. So at 60, we have, the zoom bar keeps getting in the way. 67.62. Okay. All right. So now that we've done all these tests, we can go ahead and plot them. So the best way to kind of plot these is with the scatter plot with the line. Okay. So I'm going to do that right here. So in Excel, usually I use this curve right here. So scatter with smooth lines and markers, but, you know, as long as you do any kind of scatter plot, then it's okay. Okay. So you can see from this mesh convergence test, you know, when we plot against the number of elements to the quantity of interest, you see we have this region in the front right here, which is, you know, where things are still rapidly changing. So here we don't have any mesh convergence. But once you reach this point right here for 20 elements, then things really start to level out, and we don't really see any changes after that. So you can see the ideal mesh for this one would be n is equal to 20 elements. And then anything after that will be fine as well, but then you're kind of working a little bit too hard here in order to get the results. Okay. All right. So in terms of your projects, you know, I want you guys to do a mesh convergence test for it. So, you know, I want to see kind of a scatter plot like this. Okay. So make sure you kind of know how to do this. Okay. All right. Any questions on this before we do the ANSYS example?
So for the quantity of interest, that's just kind of for our projects, we could take an arbitrary quantity as long as we're consistent with it, and then.
Yeah.
Okay.
So the quantity of interest, you know, it should be something that's going to be relevant to your design. So a lot of times, you know, finite elements is used to design a part or to perform some analysis, right? So like, let's take the it's used. So the quantity of interest is usually something that's going to be critical to, you know, what you're going to be doing with your part. So let's, you know, a lot of times when you're doing structural mechanics, it'll be the maximum stress that you observe in the model. Because a lot of times that maximum stress is going to determine whether your part will break or whether it's going to survive. So, you know, you usually pick the quantity of interest to be something that's going to be relevant to what your objective is, basically. Yeah. Right. Any other questions on this before we do the ANSYS example? Okay. So let's do the ANSYS example, right? So this is the project that I've uploaded onto Titanium. Okay. So you can, so I created the geometry within ANSYS, so you can just double click the project and it should load, hopefully. So I tested it out on my computer, but you know, things don't work out until you test it out on every user's computer. So basically, we have a geometry that kind of looks like our bike crank. So we have a part which is going to be fixed on the left side. So you can see I've applied a fixed support here, right? And on the right side, I have a force downward. So basically, we're going to have this part which is going to be in bending. Okay? And what we're interested in solving for is we want to find out what the maximum stress is in this part. So our quantity of interest is going to be the maximum equivalent stress. So you can see on the solution A6 over here, I've created a solution field called equivalent stress, right? So that's kind of similar to you know, how we did all our projects. And then basically what I'm going to use here is this value right here, which is going to be the maximum. So you can see right here, the maximum equivalent stress is going to be 736 psi, which occurs right here. And actually, let me change the units in order to be in millimeter. Right. Okay. So now our results are in megapascal. So you can see we have a stress of 273.97 megapascal. Okay. Okay. Question?
Are equivalent and von Mises synonymous?
Yeah.
With each other? Okay.
Yeah. Yeah. So equivalent stress and von Mises stress are the same. Yeah. Okay. So we're going to do the same thing we did for the Matlab example. So we're going to open up a spreadsheet and we're going to make the same graph. So our graph is going to be n, where n is our number of elements. And then on the right, we're going to have a max stress. Okay. Okay. So let's go ahead and start this. So the way we're going to refine this, as you can see on the mesh over here, I've created two objects. So I've created our method object, which I've kind of left automatic for now, just because, you know, we're mostly just going to be concerned with the sizing. And I've created a sizing object. Okay? And so the way we're going to modify this mesh is we're going to decrease this element size to increase the number of elements. Okay? Right. So I've already kind of run the first test here. So let's go ahead and check the number of elements. So remember, the way that we check the number of elements is we click on just mesh right here on the project outline. And then we go to the bottom left over here to the details, and we click on statistics. So the statistics will tell us how many elements we have. So here we have 39 elements. We can go ahead and put 39 over here. Okay. And then let's write down what we got for the maximum stress. So the maximum stress we got here was 273.97. Okay. All right. So let's go ahead and start refining this mesh, and let's see how this quantity changes. Okay. So remember, the way that we refine this mesh is that we're going to decrease the size. So if we go to the bottom left here, we can see we're starting with a mesh of 25 millimeters. So you can see, you know, just from this mesh, this is a pretty coarse mesh. So we have very few elements in here. So let's go ahead and decrease this. So let's start gradually. So let's decrease this from 25 down to 20. Okay. So then after we've decreased the mesh size, we have to update our mesh. So we can either do that by hitting update, or we can do generate mesh. So I'm going to do hit generate mesh. Then ANSYS is going to mesh the part. Right. Let me close MATLAB so I have my laptop's not crying on me. Okay. Okay. So you can see we have some warnings here. So the warnings here, some element sizes are larger than the global element size. So that's okay. So, you know, we have a very coarse mesh. So we don't expect the solutions to be that accurate here. So these kind of warnings, you can kind of, you know, have it be okay. Okay. So let's find out how many elements we have in this mesh. So let's click the mesh right here, and then let's look in the bottom left. So in the bottom left, we see we have 60 elements. So let's put in a 60 right there. Okay. And then let's run our simulation again, just so we can check the results. So let's go right click on solution A6, and we can click solve. Yeah, running ANSYS is not so easy when you're running Zoom at the same time. Okay, so we're done. Right, so we can see that our stress was significantly changed. So remember, in the last time we had a stress of 273.97. We can see now that our maximum stress is 309.22. So let's go ahead and put that in. Right. So you can see we have significant changes. So we're going to need to continue with the mesh refinement. So let's go back to our body sizing and let's change it to something lower. Right. So let's change it to 15 millimeters. Okay. So once we did that, we can go ahead and click solve. So if you change the mesh and you just go ahead and click solve, it'll remesh it for you, and then it'll solve the model right after that. Okay. Oh, so it looks like we're done. Okay. So you can see the maximum stress changed again. Okay. So let's go ahead and write down the number of elements that we have. So the number of elements that we see in the bottom left here is 92. Okay. And then our stress is 285.2. Okay. So you can see here, you know, our mesh, you know, as we refine the mesh, our quantity of interest here is kind of jumping around a bit. So it started low, then it went high, now it's down low again, right? So this is not uncommon, so this is fine. So even if your you know, values are jumping around a lot, what we're ultimately looking for is if the quantity is going to plateau. Okay. So let's change this again. So let's change the body sizing down to 10. Okay.
Does that indicate shear locking at all?
Yeah, that's a great question. So there shouldn't be any shear locking here because I should have a quadratic element. Yep. So if you were running linear elements, then that would be definitely something that you would look for. Where if you do have something like that, then you can check to see if you have shear locking based on if you have linear elements. But even if you have linear elements, if you refine the mesh quite a bit, you can kind of get rid of that shear locking. So refining the mesh is kind of like a cure-all to kind of fix all problems, but the only caveat is that it becomes quite expensive then. Yeah, good question. Okay, so the number of elements now is 225. Okay. And then let's look at our equivalent stress. So our equivalent stress is, the maximum is 293.44. Okay. Right, so let's keep going. So let's change our body sizing down to 7.5. So I did this example, before the lecture. So I kind of know the steps that I want to take for the mesh refinement. But again, this would be probably something that you would kind of experiment with and kind of try out different things until you reach convergence. Okay. So now let's see. With that, we have 393, and then our equivalent stress is 297.8. Okay, so then now let's change our mesh sizing to 5 millimeters. And then let's solve it again. Yeah, so you can see it's a little bit tedious. You're basically just changing a few numbers and hitting run and then doing it again. But this is something that's that you need to do a lot of times. Right, so now we have 854 as our number of elements, okay. And our equivalent stress is 310.78. Okay, so let's refine again. So let's go from 5 to 2.5. Okay. So you can see our elements are jumping up quite a bit. So we have 3382. And then our equivalent stress here. Yep.
Is there a reason why it's not automated?
The mesh convergence testing?
Right.
Yeah, I have seen or I've heard that ANSYS does automate something. They can automatically do it for you. I haven't personally used it myself. So I think there might be options for that. But just for kind of educational purposes, and just so you kind of have more control over how much you step on it, usually it's not bad to do it manually, especially with these kind of simulations where they only take at most maybe like 10-15 seconds to run. Doing it manually usually is not that bad. But if you are running a simulation where it takes you maybe about an hour or two to just run a simulation, then automating it I think would be something that's smart. So you don't have to sit at your computer for like 5 hours just to run the test. So you can basically run it overnight. So I'm pretty sure ANSYS does have that capability to automate a mesh convergence test. I've just personally never used it myself.
Thank you.
All right, so let's do one more. So this is going to be quite an expensive simulation. So we're going to have a mesh size of 1 millimeter. And so it's going to take a while to mesh. Actually, I'm not sure that this will run, because the ANSYS, I did this example kind of back when I had my office kind of last week, and I have kind of a better version of ANSYS there. So this is actually the student version. So I went on the ANSYS website and pretended I was a student again, just for a few, just to download it. Okay. Okay. So so I ran into the issue where I was, we had too many elements here, right? So if you look at our mesh here, we have 20,829 elements. Okay. So that was too much for this version of ANSYS to handle. So let's bump it up a little bit. So let's do 1.5.
Since we have a little bit of time to kill, in industry, would we typically be told what the area of interest is, like that DTDX, or is that something we just define or assume on our own?
Yeah, so that's that would be something that you would decide together with your engineering team, because a lot of times you're working on a part together with a group of other engineers, and then you're you would determine what that quantity of interest is, and basically where that area is. So for now, I'm kind of telling you where that is right now, but that would be something that you would decide with your company and kind of with your team to do. Yeah, great question. Okay, so someone does have the a better version of ANSYS. Since you're on your personal computers, I won't ask you how you obtained it, but that's okay. So we got a stress of 316.66. Okay. Yeah, and then with 1.5, we get basically the same thing. So so the number of elements here was 9184. Okay, so the number of elements in that case was 20,000. So we can do that one too. So we can do 20,733. So that was with the 1 millimeter case that I wanted to do, and the stress is 316.66. Right. And then this one, we got 316.38. Okay. So we can do the same as before. So we can plot this. Okay. And as you can see, here's our plot. So you can see, once we kind of reached this threshold right here, then that's when things started to converge. So this location right here was kind of the best place to run your mesh. And that was when we had 3,382 elements. All right, any questions on the ANSYS example?
Would you want us to use both the ANSYS and the Matlab convergence test for the final project?
Yeah, so for the final project, it's just going to be an ANSYS project, so it would just be the ANSYS part. So you would just do the mesh convergence in ANSYS. So I only need to see kind of one plot right here, which you developed from ANSYS.
Hey, Professor, you said at what point is convergence for this one?
Yeah, so here the convergence was kind of right here. So you're always going to be looking at your graph and kind of seeing where it starts to level out. So the first part where it starts to plateau was kind of this location right here. We can see where my mouse is. So it's the point 3382 and 316. Yeah, so mesh convergence testing, you're always looking for where it's going to even out.
That spike right there at the very beginning, does that mean anything at all? Or is that just some random Is that just a glitch kind of in?
Yeah. So sometimes, you know, this curve right here is not going to be smooth. So a lot of times you change your elements, you know, especially for the really coarse meshes, you could have the value kind of jump around quite a bit. So that's normal. So you could see things jump around. You know, here we saw it go from 273 to 309, and then back down to 285. So that's not uncommon. So you know, as long as you reach a point where things start to plateau, then that should be okay.
All right, cool.
All right. Any other questions on this? Okay. So I want to give you guys just a few pointers. So you can see from this plot right here are kind of the location where we're looking at our stresses was kind of at a bend right here. Okay. And so I picked this part kind of on purpose because you know, a lot of times when you're looking at stresses and you want it to converge, you always want to look at it at a place where you don't have a sharp corner. Okay. So you can see what I've added here was basically a fillet. So I filleted this this corner to make it kind of rounded. So if you actually, you know, if you actually go back to our previous ANSYS activity on the signpost and you try to do a mesh convergence there, it's going to be a fool's errand. Because where the maximum stress occurs on that signpost, it's going to be at a location that looks like this. So you basically have a sharp kind of corner right here, right? And in particular, you have a sharp corner that's right next to a fixed boundary condition. So, you know, if you remember from the project, where you saw the maximum stress was kind of at the bottom of the signpost where it attaches to the ground. So in those locations where you have kind of a sharp corner, or sharp edge, you know, as you know, kind of what they often call in the ANSYS community, it's very difficult to reach mesh convergence there. So that kind of gives you a little bit of hints on how you can treat your geometry kind of before you go into ANSYS. So in ANSYS, you know, anytime you have a sharp kind of corner or a sharp edge in your geometry, ANSYS is going to have a really hard time estimating quantities there, especially the stresses. So for your final project, if you're looking at a geometry and you're looking at something that has kind of a sharp corner, something like this, right? And that's going to be an area of interest for your project. So you want to, you know, you really want to compute the stresses here. You should really consider adding a fillet here or adding a chamfer so that you don't have such a sharp corner. Because with that sharp corner, you know, what's going to happen is that you're going to have a high stress concentration there. And it's going to be really difficult for ANSYS to kind of do that. Because if you can imagine, you know, ANSYS is going to try to put an element that kind of, you know, fits to the sharp corner. And it's not going to be able to compute the stresses all that accurately. So whenever you have sharp corners, it's always a good idea, whether you do it in SolidWorks or you do it, you know, in ANSYS itself, to basically put a fillet or a chamfer on those sharp corners so you don't have those basically in your model, because those can really mess up, especially your mesh convergence tests. So if we did our mesh convergence test based on this corner right here, basically we would keep refining and refining, and we would never reach convergence because it's a sharp corner. Right? So make sure you look out for that when you're doing mesh convergence tests on your final project, that you're kind of avoiding places where it's a sharp corner. And if that sharp corner is something that's absolutely critical to your model, then consider, you know, modifying that part in ANSYS or in SolidWorks where you add a fillet there, so you don't have that sharp corner.
So does that like, can you add like a tiny fillet there and it'll do the job pretty well? Like,
yeah.
Like even if you put like a half inch or whatever, half a centimeter fillet or whatever on a big part, that would still prevent that from happening?
Yeah, so I mean, the bigger fillet that you put there, the more that it would help. I mean, of course, you don't want to put too big a fillet because it's, you know, it might be unfaithful to your original geometry, but any little bit will help. Because when you have kind of that 90-degree kind of turn in a finite element simulation, and then the stress can really concentrate there. So one strategy that you can do is you can, you know, and you actually do have a sharp corner in your geometry. You can put like a tiny fillet, like you said. And then, you know, kind of a preview for kind of the last thing that we'll talk about today is you can add a refinement object around there. So make sure you refine the mesh around that fillet. And that should do a pretty good job of making sure that you don't have kind of an unnatural stress concentration at that sharp corner. Yeah, okay. Good question.
for heat transfer problems, is there like an equivalent sort of thing you should be avoiding?
Yeah, that's a great question. So, so in heat transfer, kind of the equivalent thing, you know, you should still avoid sharp corners. So it doesn't matter if you're doing structures or heat transfer. But in heat transfer, if you have a sharp corner, the thing that'll be really difficult to analyze there will be the heat flux. So a lot of times you're interested in how much heat or how much energy is going to be crossing through your model if you're doing heat transfer simulation. So the heat flux will be really difficult to converge if you have a sharp corner in your model, just like that. Any final questions before we go? We kind of bring back mesh refinement and kind of see where that's going to be useful. Okay. So if you think back to kind of the very first ANSYS activity, we did one additional thing with the mesh that we haven't seen for a while, and you know it's you'll see that it can be really useful for places like this, right? Because you can see from our equivalent stress plot that you know, a lot of times where we're interested in are places where, you know, the stresses are high, and you know, wherever the stresses are high, that's where we want good mesh density. Okay? But if we kind of zoom out from our model, you know, and you know, if we know that we're really only interested in this region right here where the stresses are concentrated, we really don't care what's kind of happening over on these other regions where the, you know, the plot is blue. So what the mesh convergence test that we did, where we refined the entire mesh, you know, a lot of that effort was kind of wasted just because, you know, we were refining the mesh in areas kind of in the kind of on the sides of these dog bones here, and it was kind of wasted effort because we don't really care what's going on there. Okay? So the thing that can really help you out in ANSYS to kind of localize your mesh refinement is to use the mesh refinement object. Okay? So let's kind of remind ourselves how to do that. So the way I do that is I right-click Mesh, and I go to Insert, and I insert a refinement element. Okay, and then here, this will basically let you pick regions in your model where you want to refine. Okay, so in this case, I just want to refine around this this curve right here. Okay, so these curves right here are edges. So let me change to the edge selector here. Okay, and then let me choose these two edges. Okay, so I held Control and I click both. I'm going to hit Apply. And then what I'm going to do is I'm going to change the refinement up to 3. Okay, so I've kept the mesh at the most coarse that it could be, which is 25 millimeters, but I've added a refinement of 3 times around these edges. Okay, and so what that'll basically do is ANSYS will basically say that the elements around the where you put the refinement will be 3 times as small as where it is elsewhere. Okay, so if we go ahead and solve this. So we can look at our mesh. So we have a really coarse mesh right now, so it's kind of hard to see, but you can see, you know, on the right side here, we have a very coarse mesh, but in the vicinity of the region where we're interested in, we start to see a more refined mesh. Okay, so we can make kind of a separate table for this. Right? And what you'll see is that when you add refinement to kind of very key areas in your model, you'll reach convergence a lot faster than if you did kind of a global refinement, which is kind of what we did. Okay? So you can see from the mesh here, we have 179 elements. So let's do a 179. And then our max stress is 301, okay, 0.1. So now it's going to go through the same exercise. So let's start to reduce this, and let's see how quickly we reach refinement. Right. So you can see already, you know, once we changed it to, you know, we have a body sizing of 20. So before that corresponded to this guy right here, right? So we had 60 elements. So here we have more because we added the refinement. So we have 287. Sorry. But you can see our stresses are a lot closer to what our true value is. So, you know, here we kind of already know what the true value is. We know it's 316. So you can see we did 317.52. Okay. So now let's refine again. So now let's change this down to 15. Right. So you see the number of elements we have is 315 now. And then the equivalent stress is 315.52. Okay. So if we change this again, so let's change this down to 10. Okay. So we can do that. We see we have 578 elements, and then our equivalent stress is 315.49. Okay. So I think we just need to do one more, and then I think we should be good to go. So you can see, we're converging a lot more quickly, right? So you can see it took for the global refinement, it took us all the way up until 3,382 elements in order to kind of start seeing convergence. Or we're already kind of seeing that with a much lower number of elements here. Okay. So you can see with that, we have 800 elements here. And then our equivalent stress is 315.95. Okay. Let's go ahead and plot this guy. So you can see we did 3 kind of simulations in a row, and we had kind of very little changes. So we're starting to have some faith that this is our converged value. Right. So you can see we have this kind of this plateauing here. So we can do a couple more if we wanted to, but after this, it's we're already kind of reached some kind of satisfactory level right here. Okay. So you can see we're plateauing. So this kind of shows that if you add refinement to kind of key areas in your model where you kind of are expecting the stresses to be maximum, or for a heat transfer case, you can add refinement to the places where your heat flux will be a maximum. That'll help you refine or reach mesh convergence kind of a lot more efficiently than if you didn't do that. Okay. All right. Any questions on the mesh refinement?
Is it possible to draw a line on your geometry to add refinement at that specific edge?
Yeah, you could. So kind of just like we did with the last activity where we made kind of a phantom surface. So
Right.
you can go into a design modeler, which is the kind of the CAD tool within ANSYS, and draw a line or whatever kind of surface that you need to kind of make sure that you can add refinement to kind of a key area in your model. So yeah, you can definitely do that. Especially if you're importing a model from SolidWorks, that might be something that you have to do in order to kind of refine in kind of the area that you want.
Okay.
Yeah. All right. Any other questions on refinement?
If you were doing this in industry, would you try to automate the system a little bit more? Like even if it was just like pulling those numbers and like having like Matlab maybe track like the derivative of your graph to find it like within your reasonable bounds.
Oh yeah, absolutely, yeah. So if you're doing this in industry, yeah, you can. This is definitely something that's very automatable because it's you're just basically changing a few numbers and you're just picking out a number and then replacing it. So there's definitely a lot you can do. And actually, I just noticed that there's an automation button up here. So you can, I think in ANSYS there's you can make macros that kind of do a lot of this stuff for you. So maybe that might be something that we do in kind of the extra activity that we do at the end. That could be something I look into. So I've never personally done it myself, but it could be something that's really useful to you in industry. So yeah, maybe I'll look into it over the spring break, and then we'll look at that. All right. Any other questions on this mesh refinement? Okay, so there's one more kind of qualitative thing that you can look for. So if you're just doing a first finite element simulation and you don't want to go through the whole thing with mesh convergence study, one kind of way that you can kind of just qualitatively look at your model and see if things are converged is you can look at the contours. Okay, so by contours, what I mean are these color patterns that are on your model. So kind of a good indication for a converged mesh is that you have these kind of very smooth distributions here. Okay? So you can see that we have this kind of smooth orange thing, this smooth yellow stripe, and this smooth green one. Okay? So you can see that even though we've already run the mesh convergence test, we know that this converged. But just by looking at kind of the smooth kind of contours here, this kind of tells us, okay, this is probably at least decently converged or decently accurate here. If you compare that to what's over here, So you can see this color contour. You can see this region of the mesh is pretty coarse. So you can see this color line right here is kind of jagged. Okay. So whenever you see kind of a jagged line like this, or you see kind of like some splotchiness in your kind of your stress results, that's kind of a qualitative indicator that maybe you should refine the mesh over here a bit more if you were interested over here. So since we're not interested over here, it's okay, so we don't have to do it. But you know, if you see jagged lines in kind of the area that you're interested in, that's kind of an indication that maybe you should refine the mesh a bit more in order to reach convergence. Okay, so we're out of time today, so that's all I got. I'm going to you know, I've been recording this lecture, so I will upload it onto YouTube so that you guys can see. So next time I see you guys will be after the spring break. So have a great spring break, everyone. Please stay safe. Please stay indoors. Don't go out unless you absolutely need to. Okay. So because you know this pandemic, I think is going to last us until the summer. So stay safe, stay healthy. Wash your hands. Okay. Don't. I've seen some YouTube videos of people going to like public restrooms and like licking the toilet, and then the next day he tested positive for coronavirus. So don't do anything dumb like that. Okay. You know, because you know, I want to make sure everyone finishes this semester happy and healthy and, you know, full of finite element knowledge. Okay. Yeah, he got arrested too. Good. Okay. All right. Also, I'll see you guys later. So I'll stick around for a little bit if you have any additional questions. But if not, you guys are free to close it. And I'll see you guys after the spring break. If you drop dead, no, if you drop dead, you do not get an A. No, no one's gonna drop dead. Yeah, so for the spring break, so I've uploaded the next ANSYS activity. So we're gonna do that together on the first day back from spring break. But if you want to take a look at it, if you want to take a crack at it, you're free to do that. But we're gonna do that together after we get back from spring break. So if you want to work on stuff over the spring break, just kind of focus on your project just for now. Right, so the question is, are we going to do any heat transfer or fluids? So I'll focus mostly on structures since I think a lot of people are doing structural things for their projects. I know a few people are interested in heat transfer, but I think I'll probably work with you guys individually on doing that stuff. Yeah. Fluids will be difficult because fluids goes through, it doesn't go through ANSYS Mechanical, it goes through a different program called Fluent. So it's packaged with ANSYS, but it's a very different interface than the one we've been working with. So fluids would be difficult, but heat transfer, it's you know, I'll probably kind of work with you guys individually if you want to do heat transfer for your project. Oh, so for the project, you don't need a strong form, but you do need what's called a simplified model. So we'll go over kind of what that is kind of after the spring break. So for some problems, if you can do kind of a strong form kind of representation, that would work well for your simplified model. But that's not going to work for everyone. So we'll kind of talk about what that is and what kind of works for people after the spring break. Yeah. So the yeah, so we're not going to do too much with heat transfer within the class. But if that's something you want to explore with the project, then I'm happy to kind of look into stuff for you and kind of work with you individually for that. All right, so I think most of the other people that are in this room are AFK. So I'm going to end the meeting. So if you have any further questions, then you guys can email me. Okay. All right. See you guys later.